Let us now start the set of exercises at the end of this section 1.3. So here in many of the exercises we will see properties of triangular numbers. Let's see what this first one. Each of these numbers 1, 3, 6, 10, which are obtained like this by adding the first few positive integers, represents the number of dots that can be arranged evenly in an equilateral triangle. 1 dot, 3 dots, 1 plus 2, 6 dots, 1 plus 2 plus 3, 10 dots, 1 plus 2 plus 3 plus 4, like that. So they can be arranged like this in equilateral triangle. And this led the ancient Greeks to call this type of numbers triangular numbers. That is, a number is called triangular if it is the sum of consecutive integers beginning with 1. So now we have to prove these facts about triangular numbers which were found by these mathematicians. That last one is by Euler. So let us see these things. There are other numbers also, pentagonal number, etc., which can be they are related to regular pentagons in much this same way, like triangular numbers are related to equilateral triangles. Many classes of interesting numbers are there. Okay, now in the first one we have to prove that a number is triangular if and only if it is of this form, and this is just nothing but the familiar formula. Which we have already proved. So we are just simply going to mention that, because you see here we will be arranging this many dots, so it will give us the nth triangular number. First you have 1 dot, then in the next row you have 2 dots, then in the row below that you have 3 dots, and so on. So for part A we just write C exercise 1 of section 1.1. So this was the very first exercise. Then in part B, the integer n is a triangular number. Integer in this context is of course a positive integer, if and only if 8n plus 1 is a perfect square. First assume that n is a triangular number. Then n is equal to m times m plus 1 divided by 2 for some positive integer and this is of course by part A. Now if we calculate 8n plus 1, then this is 8 times m plus 1 divided by 2 plus 1, and that is equal to this, which is 4m square plus 4n plus 1, which you can easily see is 2n plus 1 whole square. So if n is a triangular number, then 8n plus 1 is a perfect square. Conversely, let 8n plus 1 be equal to t square okay, there is one small issue with this part B. The integer n is a triangular number if and only if 8n plus 1 is a perfect square. Oh no, I mean okay, there is no problem. I was thinking about the case n equal to 0. In that case also 8n plus 1 is a perfect square, because in that case 8n plus 1 is 1, which is 1 square. But we are considering n to be a positive integer first, that is given, and then we are making the statement that such a positive integer n is a triangular number if and only if 8n plus 1 is a perfect square. So there is no question of having n equal to 0. Okay, so that means for some positive integer t, okay, t anyway will be positive. No? In that case also where n is equal to 0, I mean it does not occur, but still I am just saying t will be equal to 1. In that case also it is positive. So what was I thinking? No, there is nothing to think of. Okay, fine. Then what is n from here? N is equal to t square minus 1 divided by 8, which can be written as t minus 1 times t plus 1 divided by 8. Now 8n plus 1 equal to t square implies t is odd. And why is that so? You see, we know that if t is even, then t square is also even. However, the number on the left hand side is odd, because when we divide this number by 2, we get the remainder 1. Or you can also argue like this: since this number is of the form 2 times an integer plus 1, so that is why it is odd. So square of t is odd, so t itself must also be odd. Let t equal to, so because t is odd, t will be of this form 2u plus 1, where u, okay, yes, okay, fine. Now that condition that n is a positive integer will be necessary, because you see, simply saying that t is odd, fine, it has given us this form of t 2u plus 1, but there is no need for u to be positive just from this. U can be 0 also. In that case also you get t equal to 1, which is a positive odd integer. However, that will not be the case, because if t is 1, then from this equation n has to be equal to 0, but n is given to be a positive integer. So t cannot be 1, t must be greater than 1, and as such u must be not equal to 0, that is u itself should be a positive integer, where u is a positive integer. In brackets we can write, since n is positive, means n is greater than or equal to 1, we have t greater than 1, and hence u greater than 0. Now we use the value of, the expression of t here. Thus we have n equal to, so if we put t equal to 2u plus 1, then here we get 2u, and here we get 2u plus 1 plus 1, 2u plus 2, divided by 8. Simplifying this, after cancellation, we get u times u plus 1 divided by 2, 4 is there in the numerator, so we get this. Now n has the form of a triangular number, but that is not enough. U should be a positive integer, and that's what we have here. Since u is a positive integer, part A implies that n is a triangular number. So the converse part also has been proved. Okay, then part C by Nicomachus. The sum of any two consecutive triangular numbers is a perfect square. This is pretty straightforward. We just have to add two consecutive triangular numbers. For any positive integer n, we have the triangular number that is obtained by adding the first n positive integers is by part A this, and the next one is this. Okay, now before we clean this part, let's see this one also by Euler. If n is a triangular number, then so are these other three numbers: 9n plus 1, 25n plus 3 and 49n plus 6. Okay, now we can take n plus 1 divided by 2 common out, and in the first term we have n, in the second one we have n plus 2. That means n plus 1 divided by 2 times 2n plus 2. After cancellation of that 2, we have n plus 1 times n plus 1, so this is n plus 1 whole square. So that's why sum of two consecutive triangular numbers is always a perfect square. Okay, now we come to D. Now instead of, okay, so in part D, it is given that n is a triangular number. We have to prove that first of all, say 9n plus 1 is a triangular number. Now this can also of course this can of course be done directly using just part A. That is, you consider an expression of the form m times m plus 1 divided by 2. You substitute that for n because n is a triangular number, and then you show that 9n plus 1 also has that form. But as the numbers grow in size, I should not say size but complexity, 9n plus 1 is okay. After that we have 25n plus 3, so it becomes somewhat a little cumbersome to do the calculations. Instead, a very clever way is to use part B, because you see part B gives us a necessary and sufficient condition for a positive integer to be a triangular number, namely that 8 times the integer plus 1 should be a perfect square. So from the given condition that n is triangular, we can easily show that the other numbers are also triangular using this necessary and sufficient condition. So we proceed like this. Since n is triangular, by part B, 8n plus 1 is equal to t square for some positive integer t, and we are able to do this because this condition is a necessary and sufficient condition. So we are using one half of the condition here to write 8n plus 1 as a square. Then when we show that 9 times no, I mean 8 times 9n plus 1 is also a square, then we can use the other half, the converse of this, to then claim or conclude that 9n plus 1 is also a triangular number. For some positive integer t. Now 8 times 9n plus 1 is equal to what? Not just this but plus 1, because this is our integer. 8 times this plus 1, this is equal to, this will be 8 times 9n plus 8 plus 1 is 9. So that is, we have this. Now if we take 9 common out, then we are left with 8n plus 1 inside. So this is 9t square, which is 3t whole square. Like that, what is the next one? 25n plus 3. 8 times 25n plus 3 plus 1. So this is 8 times 25n plus 3 times 8, 24 plus 1, 25. So 25 times 8n plus 1. 25t square, that is 5t whole square. So that is also the square of a positive integer. This one is also one such number. And finally we have 49n plus 6. Times 6, 48 plus 1, 49. You see that there is a pattern in these numbers which is making this calculation possible. I mean, it's as if things are falling in place. So by part B again, nine n plus 1, 25n plus 3 and 49n plus 6 are also triangular numbers. So comparatively much less calculation, and that's just it. That is the first solution. Then 2. if Tn denotes the nth triangular number, we are going to use this notation throughout this book. Wherever triangular numbers appear, Tn will denote the nth triangular number. So for example, T1 is 1, T2 is 1 plus 2, that is 3, T3 is 6, T4 is 10, and so on. So this is the nth triangular number. Prove that in terms of the binomial coefficients, Tn is n plus 1 choose 2 for all positive integers n. And this is just we have to write the formula for the binomial coefficient that is given, and we have to see that it becomes equal to Tn. For any positive integers, we have if we use the actual formula, actual expression for the binomial coefficient, then we get 2 factorial divided by n plus 1 minus 2 factorial. So this becomes n plus 1 factorial divided by 2 factorial times n minus 1 factorial. So that is n plus 1 times n minus 1 factorial in the numerator, and in the denominator 2 factorial of course is 2 and n minus 1 factorial. So this is n times n plus 1 divided by 2, which by part A is the nth triangular number. We will not refer to part A means part A of the previous exercise. We will not refer to it because this is something that is we already know it so well that if we add the first n positive integers, then this is an expression for the sum. Then exercise 3. Derive the following formula for the sum of triangular numbers. Attributed to the Hindu mathematician Aryabhat. $580. He gave us this formula for adding the first n number of triangular numbers. And the sum turns out to be n times n plus 1 times n plus 2 divided by 6. There is a hint also given, although we will not use the hint. Group the terms on the left hand side in pairs. Noting that tk minus 1 plus tk equals k square, which we have already seen in exercise 1, namely in that part where we showed that the sum of two consecutive triangular numbers is a perfect square. Anyway, we use induction. If you want, you can follow the hint also. We are using induction as much as possible because it's not always very easy to use induction. So whenever you can, you should use induction if you want to save time. But if you really, you see, there is a disadvantage also in using induction. Induction actually never tells you what is going on in the identity that you are trying to prove by induction. It bypasses everything, and if you are able to carry out the induction step from the induction hypothesis, then you have logically proved the identity. However, this will not tell you why the identity is actually true, because a large part of why the identity is true has already been assumed by you in the induction hypothesis. So you just have to carry out the induction step. Sometimes the induction step becomes very difficult. So in that case, you have to look for other, maybe proof by contradiction or some sort of direct argument. But if you want to really understand what is going on inside this sum and why the formula is like this, then you should follow the hint, which however I leave to you. verifying that something is true is one thing, and understanding why it is true is often an entirely different thing. We apply induction. Note that when n is 1, then the left hand side of this formula is t1, and t1 we know is just 1, which also is equal to the right hand side when n is 1. Because this is 2 and this is 3, so 2 times 3 divided by 6 is 1. So the given identity is true when n is equal to 1. Now we assume that it's true for some positive integer n. Then the sum of the first n plus 1 triangular numbers is equal to this part. Of course, according to our assumption, this part is equal to n times n plus 1 times n plus 2 divided by 6, and we know the expression for Tn plus 1, which is n plus 1 times n plus 1 plus 1, that is n plus 2 divided by 2. Okay. Now we can take n plus 1 times n plus 2 divided by 6 common out. If we do that, then in the first term we have n left. In the second term we should have 3, because when we multiply this with 3 we should get this, and this is just okay, if you want you can write it in the showing everything, that is n plus 1 times n plus 1 plus 1 times n plus 1 plus 2 divided by 6. So the given identity is true for n plus 1. Hence by induction it is true for every positive integer n. Okay, then 4. Prove that the square of any odd multiple of 3 square of any odd multiple of 3 is the difference of two triangular numbers. And more specifically, precisely this, that odd multiple of square of an odd multiple of 3, so 3 times 2n plus 1 whole square, that is 9 times 2n plus 1 whole square, is t9n plus 4 minus t3n plus 1. What is n in this context? N of course is an integer, but can n be 0? It can be, no? Because even when n is 0, we have t1, which makes sense, and here we have t4, and here we have just 9. So we don't have to bother about n. This, however, we will not prove by induction, because we have only 2 terms and we have expressions for these triangular numbers, so we can do direct calculation. Okay, so if we use the expressions for the triangular numbers, this will be 9n plus 4 times this plus 1, that means 9n plus 5 divided by 2 minus, for this one, 3n plus 1 times 3n plus 2 divided by 2. Now if one does all the multiplications, everything, one eventually comes to this expression 72n square. These details, of course, I am leaving to you because they are extremely straightforward. You just have to carefully do the multiplications. So this gives us 36n square plus 36n plus 9. And if we take 9 common out, then we have 4n square plus 4n plus 1. So yes, we are getting what is said or what is given here. So that's just it. And then fine. These first few exercises of course are not very exciting or interesting, but the further we go down the path of number theory, the more involved naturally things will get and the more interesting also they will become. In the sequence of triangular numbers, find the following. So there are 3 parts to this. 2 triangular numbers whose sum and difference are also triangular numbers. Whose sum and difference are also triangular numbers. B. I need ink. Three successive triangular numbers whose product is also a triangular number, or whose product is a perfect square. Okay, and finally C. Three successive triangular numbers whose sum is a perfect square. So here it's just a matter of trying, looking at the first few triangular numbers and trying to come up with such examples. Usually it does not take much time. I mean, it's not unduly complicated in the sense that if you spend some time on it, the first few triangular numbers will give you the desired examples. You don't have to go very far in the sequence of triangular numbers to find these things. And one such solution is this. Without writing too much, we just directly write the things. The fifth one and the sixth one, T5 and T6, are 15 and 21. So if you add them up, you get 36, which turns out to be the 8th triangular number, T8. And if you take their difference, then this is 6 and 6 is your T3. So these are two triangular numbers whose sum and difference are both triangular numbers. And besides that, you see that they are actually consecutive. Consecutive in this sense that T5 and T6. Okay, then in part B we have, if you take the product of T3, T4 and T5, then this is 6 times 10 times 15, and that is 900, which is 30 square. So these are three consecutive triangular or successive triangular numbers whose product is a perfect square. And in part C, you can add T5, T6 and T7. So 15, 21 and 28. That is 64. Simultaneously, let me also see whether the calculation is correct. Yes. So this is 8 square. That's just it. You can find, if there are other examples also exist, you can find them also. Then exercise 6A. If the triangular number Tn is a perfect square, prove that T4n times n plus 1 this triangular number is also a perfect square. If we just simply, let me digress for a moment. looking at the many exercises in number theory, when we will see them, we will come to the realization that although the sequence or the set of positive integers is so straightforward, but if you restrict yourself to just this system, along with, of course, addition and multiplication, these binary operations, then here itself you have so much that multiple lives can be spent on just this, and there are huge unsolved problems here itself. So that gives you an idea of how vast mathematics itself is. Number theory itself is one of the most ancient parts of mathematics, and that is unimaginably vast, but there are of course other things. And the most mysterious are of course the prime numbers or their distribution in the number line or among the integers. Related to which there is of course that famous $1 million unsolved problem, Riemann hypothesis. People are still trying. Is also a perfect square. So this is part A. Then part B, use part A to find three examples of squares that are also triangular numbers. This is elementary number theory, where we will use elementary number theoretic techniques and results to find facts about numbers and other related things. But if one goes very deep into the subject, then there are those two huge areas in number theory. One is algebraic number theory and the other is analytic number theory. We will talk about those things later. Okay, so now it is given that Tn is a perfect square. Let Tn be a perfect square, then T4n times n plus 1 is equal to four n times n plus 1 times 4n times n plus 1 plus 1 divided by 2. Okay, so this is equal to, let me write here, Note that this expression can be written as this times 4n square plus 4n plus 1. So this part is Tn, this is 4, and this part is 2n plus 1 whole square. So 4 is a square, 2 square, and this is, we can see it's a square, and Tn according to our assumption is a perfect square. So this itself is a perfect square. So this is part A. Then part B. This is one of the very nice things about this book. It will, in many of the exercises you will see this pattern, that there are parts where one part is theoretical. It will ask you to show something, and then using that some other parts are numerical in nature. You can then find things using that theoretical part. So this is one such exercise. Using this we can find using one triangular number that is square, more triangular numbers which are also squares. Note that T8 is 36, which is 6 square. So two other triangular numbers that are perfect squares are 4 times 8 times 8 plus 1, which is T 220, 288, and 288, and this in turn then can be used to have this triangular number which is also a perfect square. Clearly, if you continue this process, you will get infinitely many triangular numbers which are perfect squares. However, they likely will not cover all the triangular numbers which are perfect squares. They will only give you some of them, although infinitely many. And this turns out to be 332928. Seven. show that the difference between the squares of two consecutive triangular numbers is always a cube. Between the squares of two consecutive triangular numbers is always a cube. So many hidden relations. For any positive integer n, we have difference between the squares of tn plus 1 square minus tn square. Shall we use a square minus b square formula to simplify things? Will that? Okay, let's just directly write the things and then we will see. N plus 1 times n plus 2 divided by 2 whole square minus this. Okay, so we can take n plus 1 whole square divided by 4 common out, and we will be left with what? N plus 1 whole square minus n square. And this gives us what? N square plus 2n plus 1. Oh, what? Have I made a mistake here in taking the term outside? N plus 1 whole, oh sorry, what the hell? N plus 2 whole square. Okay, so n square plus 4n plus 4 minus n square, so that means 4n plus 4, and you can see after cancelling 4, n plus 1 whole square times n plus 1, so this is n plus 1 whole cube. So it's a perfect cube. Then 8, 2 more are there, so let's just complete this set of exercises. Prove that the sum of the reciprocals of the first n triangular numbers is less than 2. That is this is less than 2. This hint we will use immediately. Observe that because we have reciprocals of triangular numbers. So for example, if you consider this reciprocal and use this expression for the nth triangular number, then you get 2 divided by n times n plus 1, and that is equal to 2 times 1 over n minus 1 over n plus 1. For any positive integer n we have. By now you can see that we had to write this many times for any positive integer n. To save us from this repetition, we will often just simply write n greater than or equal to 1. If nothing else is mentioned, then you have to assume that n is an integer. If some variable is something other than integer, then that should be mentioned, because at least in elementary number theory we will be mainly dealing with integers, that too positive integers. We have this is equal to 1 plus, now we can use this 2 times 1 minus 1 over 1 over 2 minus 1 over 3. So 2 divided by 6, which is 1 by 3, plus 2 times 1 over 3 minus 1 over 4, plus 2 times 1 over 4 minus 1 over 5. Like that, the last one is this. Now you can see there are many terms that will get cancelled. For example, minus 2 over 3 plus 2 over 3, then minus 2 over 4 plus 2 over 4, minus 2 over 5, in the next term you will have plus 2 over 5. This way, if you do all the calculation, all the cancellations, you will be left with 1 plus this term will be there, 2 divided by 2 will be there, so that will give us 1 and another 1, so this is 2. The other intermediate terms get cancelled. In fact, this 2 over n also gets cancelled. We are only left with minus 2 over n plus 1. Okay, now we are subtracting a positive quantity from 2. So if we don't subtract, then we will have 2. So this will be less than 2, and that's how we have shown what we had to show. Now there is a consequence of this fact, this inequality. If you are not familiar with infinite series, then just ignore this part, what I am going to say now. You look at this inequality. This inequality is true for all positive integers n. Now, if one considers this infinite series, six, 10, etc., that is this infinite series, which is the series where the nth term is the reciprocal of the nth triangular number, then this inequality tells us, or rather I should not say inequality, but infinitely many inequalities, because as n changes you get many inequalities. They tell us that the sequence of partial sums of this series, that is bounded above by 2, and the series is a series with positive terms, so it is convergent. This series is convergent and its sum is some real number that is less than or equal to 2. It's just an observation. And then finally we have come to exercise 9. A. Establish the identity Tx equal to Ty plus T set, where these are of course triangular numbers. X is n times n plus 3 divided by 2 plus 1. Y is n plus 1. Z is n times n plus 3 divided by 2. No plus ones. And n is greater than or equal to 1. You see, this is one such instance where we are not saying that n is an integer. It is understood n is a positive integer. Thereby proving that there are infinitely many triangular numbers that are the sum of two other such numbers. And there is a part B also. Find 3 examples of triangular numbers that are sums of 2 other numbers. That are sums of okay, so part A is just we have to verify this that this formula is or this relation is true. We have ty plus tz equal to the previous inequality. It is a little surprising the first time when one sees it, or this type of things, that although we are adding more and more reciprocals, I mean you can add as many reciprocals of triangular numbers as you want, so the sum is increasing because we are adding positive real numbers, 1 over t n, then the next one 1 over t n plus 1. No matter however small it is, we are adding something positive. So the sum is increasing the more number of terms you take in that sum. But no matter how many terms you take, the sum is always going to be less than 2. The thing is that the more terms you add, you are actually adding not the same amount, but the thing that you are adding, they are decreasing because Tn is increasing as n is increasing, so 1 over Tn is decreasing in such a way that the sum never goes beyond 2. So that is a somewhat a little surprising when one thinks of it for the first time. Okay, so ty plus tz, that means this is our y, so ty will be n plus 1 times n plus 2 divided by 2 plus t, or z itself is this. Times plus 1 So the first term is n square plus 2n plus n is 3n plus 2 divided by 2 plus whatever else we have. Okay, now this first quotient can be written as n times n plus 3 divided by 2 plus 1 because these first two terms give us n square plus 3n, I mean n times n plus 3, and 2 divided by 2 is 1. Okay, now you see we have a common term. So if we take it outside, and in fact not just that but 1 over 2 also along with that outside, so that in the first term we have 2 here, plus we have taken outside this one and 1 over 2, so n times n plus 3 divided by 2, and this is equal to 1 over 2 this plus now watch this carefully, this 2 can be written as 1 plus 1 now this is t this times this plus 1 divided by 2, so that is tx. So this is our part A. Then in part B we have been asked to find 3 such triangular numbers which are sums of 2 other triangular numbers. So you can find such things by putting small values of n. Since we have to find 3 examples, so we will put n equal to 1, then n equal to 2 and n equal to 3. If we put n equal to 1 here, what do we get? 1 plus 3 is 4, and this, of course, this one gets vanished. 4 divided by 2 is 2, 2 plus 1 is 3, so that means when n is 1 then x is 3. When n is 1, y is 2, plus when n is 1, this is 1 less than z is 1 less than x, so 2. So T3 is T2 plus T2. T2 is what? 1 plus 2, 3. So 3 plus 3 is 6. T3 is 6, yes. Like that, if we put n equal to 2, okay, let us see here, 2 and 2, they cancel each other, 2 plus 3 is 5. So that means 5 plus 1 is 6. So T6 is equal to T3 plus T5, and in fact we can start like this. We have this, and if we put n equal to 3 here, then 3 plus 3 is 6, 6 divided by 2, 3, 3 times 3 is 9. So T10 equal to T4 plus T9. T3 is T2 plus T2, T6 is T3 plus T5, and T10 is T4 plus T9. And you can see that by taking higher and higher values of n, you can generate infinitely many such triangular numbers, each of which is a sum of two other triangular numbers. So this concludes this set of exercises. So chapter 1 is totally over, which are of course preliminaries. Now we can, after this we can go back to our usual parts in number theory, usual places. So that will be all for tonight. Tomorrow we have graph theory. So tomorrow I will try to complete the ongoing section on connectivity. Let us see if we can do that. Okay, so see you tomorrow. This is me, Lucifer, from a mathematical room. Have a nice night.